We should be at you should have a screen that shows PHCC Educational Foundation webinar. And as we move from there, the next slide that you should be seeing on your screen is essentially the outline for today's presentation. And obviously that is me. I'm a piping applications for CDA, and for most of the presentations that we present, in order to provide continuing education credits, we have to have what are known as learning objectives. These are the learning objectives for this particular presentation. I will try not to read slides because I think that's a rather bad way to do things. So those will be the learning objectives for this particular presentation. There are a number of articles and publications that are available either through copper.org or through the internet. Two of those that are available through CDA are the Copper Tube Handbook. That one you can either get in PDF format directly from copper.org. Once you go to copper.org, you can also download that as an app for your Android device or your iPad or iPhone. Another PDF that is available from our website is the Recommended Practice for Soldering of No-Lead Copper Alloys, which contains a ton of information on the proper procedures for soldering and brazing of copper and copper alloys, especially those that are of the no-lead mixture, if you will. To give you a little idea who CDA is, what we are, and what we do, we're a not-for-profit trade association represented by all of the manufacturers and producers of copper and copper alloys in the U.S. I deal specifically out of a group known as the Building Construction Group. We provide information to engineers, architects, specifiers, designers for pretty much all of the building construction trades that have any involvement with copper or copper alloys. And as the not-for-profit trade association for the U.S., we represent only those domestic producers and manufacturers of copper and copper alloys. Essentially, that's the most noble form of copper. That's the wall starts out. That's a piece of copper ore coming out of one of the large mines in the U.S. That happens to be in Salt Lake City. Give you an idea, that one's about 3.5 miles across horizontally from where your toes would be to the other side is about 2.25. And from the very bottom of the pit to the top of the pit, you could probably stack about 2.5 Sears towers, one on top of the other, and they wouldn't stick out the top. Once it comes out of the ground and they process it, make a number of alloys and other things, wire, cable, strip, plate, bar, tube, pipe, and fittings, probably all of the coinage that you carry in your pockets also have some amount of copper in them. Pretty much that's what CDA is. What we do for the industry and what we do in the field, we provide technical assistance, and most of what I do day in and day out is installation training, troubleshooting, and provide technical assistance to, like I said before, engineers, architects, specifiers, and designers. We actually do all of that using our project managers out in the field. I'm located in Gettysburg, Pennsylvania. We have another gentleman, Harold Moret, located in Sarasota, Florida. Another gentleman, Craig Thompson, who's located just outside of Chicago, and Larry Peters, who is located just outside of Atlanta in Decatur, Georgia. And during any portion of the presentation, if you have a specific question, type it up. I'll try to get to those as quickly as I can. There is a lot of information to be provided, so we may end up having to wait till the end to get to those questions, but I'll do my very best to answer every one you direct towards me. The big deal on no-lead copper alloys, the what and the why. It all started with the Safe Drinking Water Act, and originally the Safe Drinking Water Act, pre-January 4th, 2014, limited the amount of lead that was permitted in solders. We all know that because we weren't able to use 50-50 anymore. And it limited the amount of lead that was permitted in any castings. That would be fittings, valves, backflow preventers, any of those copper or copper alloys, which most guys call brass or bronze, limited the lead content to a maximum of 8% total. After January 4th of 2014, things changed considerably based on the reduction in lead law, which you're looking at right there. Those 2 pages are what made all of the changes in the amount of lead that's permitted in anything that comes in contact with potable water. And what it did was it reduced the amount of lead in any castings, that being valves, fittings, backflow preventers, anything that would be what we would call a brass or a bronze. We here at CDA would rather call those I don't know why that did it. What we would sooner call cast copper alloys. What it did was it changed the maximum from 8% to a maximum of 0.25% lead in the weighted average of that portion of the component that actually comes in contact with the potable water. And there are some exclusions, which is a little confusing to some, even some of the wholesalers out there. One of the exemptions is for pipes, pipe fittings, plumbing fittings, fixtures, you name it, as long as it's going to be used exclusively for non-potable services, it doesn't have to meet the lead law. Another exemption is where it is not anticipated to be used for human consumption. One of the exceptions that are listed is for any valves, and those are main gate valves 2-inch and greater in the water distribution service. When that question was directly asked to one of the EPA people, they said that that was for those mains out in the actual service that supplies the water to the homes or the businesses or whatever, and not necessarily what we as a plumber would know as direct distribution piping. What you're looking at right now is the calculation that is required to determine what the total content is. You don't have to worry about that as an installer. That is all taken care of through NSF 61NXG and NSF ANSI 372. Get a lot of questions on exactly where does the lead come from. Why is there lead in some of the plumbing products? And it all starts out from most of the copper alloys. In order to be considered a copper alloy, that alloy must contain at least 50% copper. And into that copper, they start adding other elements that provide strength, corrosion resistance, machinability. You can actually change the color of what we would know as a copper penny to something that looks almost just like stainless steel or white metal, just by adding several different elements. The big one that everybody had to deal with was lead. Lead had a lot to do with the machinability and the wear resistance in those copper alloys. Big deal was they wanted to get rid of it, and when they took that out of those various alloys, it caused some problems and it caused some heartache for installation because some of the installers had some difficulty actually making solder joints. If we look at the existing copper tube, pipe, and fittings that we normally use day in and day out, which would be standard copper tube and wrought copper fittings, like you're seeing right there in that picture, those are 99.9% copper and silver combined, and I'll guarantee you there's very little silver in any of them. Into that they add somewhere between 15 parts per million and 40 parts per million of phosphorus so that they can draw into long straight lengths. So essentially there is no lead at all in any copper tube or any wrought copper fittings. Those 3 copper tubes that are listed, ASTM, B88, 280, and 819, are all manufactured from alloy C12200, which is a no lead material because there is absolutely no lead in the alloy. If we look at the cast copper alloy fittings, ASME B1618, this group of alloys here that are provided with a 5-digit number, every copper alloy is provided a 5-digit number, of which now there are about 896. These copper alloys that are listed right here are the ones that are mentioned in the B1618 standard. And if we look at the elements that are in these particular that can be used for cast copper alloys, you'll notice that there are a number of those that contain greater than the 0.25% lead. So these top three would probably be alloys that would not be used for backflow preventers or valves or fittings or anything else. We look at some of the alloys that are being used for products to meet the no lead law. We look at one of the big ones out there, which is EcoBrass. You'll notice it has 0.09% lead, well below that the 0.25. We look at another one that's 69300. That one is another one that seems to be picking up a lot of traction and use. That one here again has below that maximum limit of 0.25. Yellow brass, which is the same as what most plumbers would know as yellow brass nipple, is one that has a maximum allowable lead content in it of 0.25. So it is considered to be a no lead alloy. We look at some of the really exotic no lead alloys, if we want to call them exotic no lead alloys. You'll notice that there are a lot of maximum and minimum elements that are part of some of these additional alloys, even though they are, this particular one is below that 0.25%. One of the other big ones that is being used now is what's known as a copper bismuth alloy. That one has 0.25% maximum lead content allowable. The other thing that you need to keep in mind is every week, every month, there are additional copper alloys being developed by metallurgists and chemists, if you will, in order to meet the requirements for specific manufacturing processes. So we're probably going to see a number of other alloys being developed to meet these new requirements. The big deal today is trying to explain what's going on with respect to soldering some of these newer no-lead copper alloys. There is a standard out there, which is the ASTM B828 standard. It is listed in every major model plumbing code as the process and procedure that needs to be taken in order to make soldered joints. Big question is, how are you taught to solder? Most guys, if I was to ask that question, the common soldering process normally ends up looking something like this. If this was a horizontal joint, most guys were taught that you put the heat on the bottom, you put the solder on the top. When the solder runs out the bottom of the joint, you pretty much figure you have a fairly good joint. That's if it's a horizontal joint. Biggest problem is there are some faults and failures that occur because of that process. One of the things that's very difficult for installers to understand is the only thing that causes that particular alloy to melt is its ability to absorb heat from the tube, the fitting, and capillary space. All of those components have to be at the temperature to melt the alloy to its full liquid state. So this particular process, which many of us have been using, probably is not the best way to go. Actually, it is probably one of the worst possible ways to make a solder joint, especially with the newer no-lead alloys. If we were to look at this joint in a vertical down position, which most guys think is the easiest way to make a joint, and a lot of us were taught put the heat on one side and the alloy on the other side, you end up getting a rather large void on one side when you use that process, and you stand the ability to trap flux or reduce the ability to get full flow of the solder alloy into the joint. Here again, not the best way to make a solder joint. One of the biggest problems is if you start out by heating the fitting, you tend to want to increase the size of that fitting. It expands. And when it expands, it increases the capillary space. That capillary space is nothing more than an airspace, which tends to be just like an insulator, which reduces the ability to transfer heat through the fitting, through the capillary space, and into the tube. A much better application of heat would be to start out by preheating the tube. If we preheat the tube first, we actually reduce the capillary space. We actually reduce that airspace that causes the inability to transfer heat well between the fitting, the capillary space, and the tube. So it has always been a recommendation in the ASTM V828 standard to preheat the tube first and then begin preheating the fitting. The other problem that you have by preheating the fitting first with the newer no-lead copper alloys, and there's a slide coming up about 3 or 4 from this one that will actually show that they are very, very poor at transmitting heat. One of the other problems that a lot of installers have is back in the old days when they still had 50-50 and some of the other solders that had a very, very wide pasty range, they wanted to try and make those joints with the alloy in the pasty range, not in the liquidous range. Well, if we look at what actually causes that alloy to get into the capillary space, it's nothing more than capillary action. And an easy example of that is, if I was to take a pan, fill it up with red food coloring, take 2 pieces of glass and drop them down into that red food coloring, and that's 2 pieces of glass kind of sandwiched together. If I were to put a toothpick in one side of that particular 2 pieces of glass, once it was dropped into the red food coloring, just by nothing more than capillary action, the adhesion and cohesion that occurs by capillary action, that water would go up in between those 2 pieces of glass. Exactly the same process that gets the molten alloy back into the capillary space in a solder joint. Now that's very, very liquidous, almost like water. If we were to take that same example and fill the bottom of that particular pan up with Aunt Jemima pancake batter and drop 2 pieces of glass into that, there would probably not be any pancake batter go up into between those 2 pieces of glass, which means they would not fill with the pancake batter, which is the same type of problem that you have when you're trying to fill the capillary space with solder alloy in that pasty range or that pancake range with that most plumbers try to get so they can get that really nice cap on the outside of the joint. We were to look at the melt temperatures of most all of the solder alloys that are out there. These are ones that are listed in ASTM B32. You'll notice that they have melting ranges somewhere 400 and some odd degrees. Some of them will go all the way up to 700 degrees. This top number, or the highest temperature number, is that temperature that takes to get that alloy all the way to its full liquidous state. So with these new no-lead copper alloys, if we can reduce the temperature or use alloys that have a lower liquidous temperature, we stand a much better chance of getting a much better soldered joint. We were to look at the heat transfer coefficient for most of these copper alloys as compared to copper tube. We were to look at plain standard ASTM B88 seamless copper water tube, which is manufactured from alloy 12200. It has a coefficient of 196. Essentially, the higher the number, the easier it is to transfer heat. So if the copper transfers at 196, and we were to look at some of the alloys that are most commonly used, which are the eco-brass and the some of these bismuth alloys, you'll notice that especially the eco-brass has a coefficient of thermal conductivity almost equal to that of black steel pipe, which makes it rather difficult to transmit heat through the fitting. It's just a very, very low heat transfer material. So if we were to look at the 828 standard, there are a number of steps that are listed within the standard. Those are popping up on the screen right now. If we were to look at what CDA has taught for about 40 years, we had what we've always called our 6-step method of making a solder joint. And those basic 6 steps are, if you use those steps in that order, you should have no problem making good soldered joints. The first 4 steps, measure, cut, ream, and clean, are the same. Doesn't matter whether you're going to solder the joint or braze the joint. Where things get a little different is the fluxing step. There has been some discussion that there are certain fluxes that should be used and certain fluxes that should not be used for making no lead copper alloy soldered joints. The testing that CDA has completed shows that almost any one of the solder fluxes, paste fluxes, and almost any of the solders will work well together when the ASTM B828 standard is used. The next step is the apply the heat in the alloys step. Obviously, you need to use the right size torch. One of the things that we noted when we were doing some field investigations was a number of installers were using torches that were way too big for the size of the tube that was being installed. The big number that everybody needs to try and remember is 840 degrees. If it takes less than 840 degrees to melt the alloy to its full liquidous state, it's a soldering process. It takes more than 840 degrees, it's a brazing process. There are a lot of joints out there right now that are approaching 840 degrees, especially with no lead alloys, and a lot of the flux is being burnt, and anybody that's made very many joints knows that once you burn the flux, it's almost impossible to make a decent joint. Obviously, the tube has to be socketed all the way to the back of the cup. It has to be cut square, socketed all the way to the back of the cup. That lap length for any of those fittings, which is the length of the solder cup, is set by standard. Obviously, a 4-inch joint is going to have a longer 2-inch or an 1.5 inch joint or a 1/2 inch joint, simply because of the forces that can be developed. The ideal capillary space, somewhere between 2/1000ths and 10/1000ths of an inch. And normally you're going to find that it's going to be somewhere between 4/1000ths and 6/1000ths of an inch is the normal capillary space dimension. And if we were to look at what actually makes a good solder joint, as determined and stated by AWS, which is the American Welding Society, they say that as long as you get about 70% fill within the entire capillary space, which would account for no greater than 30% voids, and the voids are not interconnected, you should have a very good solder joint. And that comes directly out of the AWS soldering manual, and it comes right in this area of this particular page, is where it says that a good solder joint is one that contains somewhere between 70 and 90% fill. If we were to look at the process that we should be using for making any solder joint, it doesn't matter whether it's a horizontal joint, vertical up, vertical down. The demonstration and the slides that I'm going to use today are all based on a horizontal joint. The reason for that is if you were to ask most plumbers where the greatest number of solder joint leaks occur, and if they were honest, they would say that most solder joint leaks occur somewhere between 10 o'clock and 2 o'clock across the top of a horizontal joint. So we're going to explain how to make a good solder joint based on a horizontal orientation. So obviously what we want to do is we want to start preheating the tube first so that we can get heat back into that capillary space. We'll heat out onto the tube from the face of the fitting about as far as the tube sockets back into the fitting. And we'll heat up to about 2 o'clock on the tube, up to about 10 o'clock. We'll do the exact same thing on the fitting, starting on the bottom. We'll start, once we've preheated the tube, and we start to see the flux start to get active on the face, we'll start preheating the fitting. We're not trying to get it up to the soldering temperature. We're just trying to get it to that preheat temperature. All right? And there's a number of YouTube videos and that are out there. Some are good, some are bad, some are not exactly correct. But you have to do very little preheating across the top of the most solder joints. Half, 3/4 inch, inch and a quarter, inch and a half. Very little preheating across the top, simply because the amount of heat that you get wrap around from the torch that you're using to make the joint. Pardon me. So we're going to start out preheating the tube. It's extremely important so that we can start getting heat back into the capillary space. Preheat the fitting, and then we want to start adding alloy. We will always start adding alloy slightly off of 6 o'clock or slightly past 6 o'clock from the bottom of the joint. And we'll follow the torch all the way up the tube. We want our alloy to follow the torch because the heat from the torch will cause the alloy to melt, because the alloy is going to absorb the heat from the tube, the fitting, and the capillary space. And one thing that you'll notice in this particular picture is the solder alloy is nice and straight. Most of us guys, especially us old gray-haired plumbers, first thing we used to do was bend it in a 90-degree angle and then try to add that to the tube and the fitting, to the joint. We've found that if we can keep the alloy straight, we can tell how fast it's melting, which tells us whether or not we're putting too much heat into the joint or not enough heat into the joint. The other thing is the position of the torch. It needs to be understood that around the outside of this flame there is a secondary air. It's actually drawing air around the outside of the flame, especially with the swirl tip type torches. They have a very, very high flame velocity. They'll draw a great amount of air around the outside of them. So if I have my torch only about halfway back the fitting cup, I very well may not get alloy flow all the way to the back of the cup, because I'm actually pulling cooler air around the outside of this flame. So if I want my alloy to go all the way to the back of this cup, I want to get my torch all the way to the back of the cup. That should give me 100% penetration, and ideally, if I'm using the right process, I should get 100% penetration with 100% fill. Ideally, that's what we want to get. Now, if we were to look at this process, and you have to bear with me, using PowerPoint, I can't make it nice and smooth, but if I was already completed preheating the tube, preheated the fitting, I'm getting ready to make the solder joint. If I start at this point with my torch, I would want to start adding alloy somewhere in this area. And I want to follow my torch the whole way up this joint till I get just about to the 12 o'clock position. What I don't want to do in a horizontal joint is I don't want to allow that alloy to roll over the top of the joint. If I allow it to roll over the top of the joint, I stand the probability and the possibility of trapping flux behind it. Once I get it just about that 12 o'clock position, I'm going to want to go back and melt out right here and start adding alloy at this point right here. Follow my torch up that side of that joint again. Now, if I'm using total heat control, I'm melting the alloy just at the right rate so that it's not just dumping out and rolling out on the ground, getting a lot of drips and drops. All of this alloy below from about 3 o'clock to 9 o'clock should be fairly solid. As I go from this point on up the joint, heat transfer is going to start causing some of this alloy to melt. And as I'm feeding molten alloy in this area as I come up the joint, what we're actually doing is we've developed a solid dam of solder on the bottom of that joint. So as this alloy starts to melt and this alloy starts to melt and drop back because of gravity, for lack of a better term, it's going to build up on this solid dam of solder and continually fill that joint. Once I get to the top, I want to continually fill and feed alloy until I see drips come out here and drips come out in this position over here. That tells me that the joint is full of solder, and that's what I want. I want a joint that is completely full of solder. Now, if we were to look at the progression of this, making this particular joint, you got to work with me a little bit today. I understand that these are wrought copper fittings, and not cast copper fittings, but it's the same process. Wouldn't matter whether it was a valve, a fitting, a flange, whatever. You're going to have the torch in a position where the flame goes from the back of the cup out onto the tube to keep the tube hot, and you're going to work your way up the joint. Where a lot of guys have a problem, especially in T's and 90s, is when they get to this point, if they're trying to get the torch flame right out across space, you end up with a little bit of a bind, and you tend to want to pull the torch back and tends to want to throw the heat out over the top. Little problem. What you need to do is just turn that torch a little bit so that you're sure that you're getting enough heat to the back of the cup in order to melt that alloy all the way to the back. We don't have to worry about the little drip on the bottom. We can get rid of that when the joint's completely done. This little drip right here, if we take the torch right down the face, we can melt that off, knock it off with the alloy, and we're done. Since you can't see what happens on the inside of the joint from the outside of the joint, we're going to do this one in X-ray form. We've already preheated the tube. We've already preheated the fitting. We're going to get that torch all the way to the back of the cup. We're going to start feeding alloy a little off of 6 o'clock, and that alloy will always flow in the direction of the greatest amount of heat. So as I work my torch up and my alloy, I always want my alloy behind the torch. And as I get closer to the top, what I'm doing is I'm actually pushing flux ahead of that solid alloy. So I've got flux developing right here. I'm pushing alloy in and pushing the flux out. And once I get up the other side and get ready to start driving alloy in the top, it takes a little bit of technique on these horizontal joints to actually drive enough alloy in so that you can drive the flux out and not end up with a large flux pocket on the top of the joint. Well, let's see what happens if we get a little bit confused or we don't move the torch. We started out perfectly fine. We preheated the tube. We preheated the fitting. We start feeding alloy right where we're supposed to start feeding. But I kind of hold my torch in one location, and I allow my alloy to get ahead of my torch. What ends up happening is I start trapping flux in this area right here, and as I drive alloy in, it tends to want to push that flux up. They don't necessarily, the solder and the flux don't necessarily mix very well. So the flux that's kind of driven to the back of the cup here, it'll give you an appearance of what looks like bubbles or boiling at the face of the joint. And in a lot of cases, that's that flux material trying to push itself out through that very, very thick, if you will, solder alloy. Once the joint is done and you're sure that you don't have any more molten alloy in the joint space, you want to take a dry rag and wipe any of the flux that was pushed out of the joint during the soldering process off of the tube and the fitting. You don't ever want to quick quench a solder joint because you stand the ability to cause the solder joint to crack by nothing more than that rapid contraction of the joint. Imagine, if you will, you're using a solder that has a melt range somewhere between 420 and, let's say you're using one that goes all the way to 660 degrees. It'll be solid somewhere around that 420, 425 degree range once the joint is completed. If I took a wet cold rag and threw a wet cold rag on top of that joint, this alloy that would made up the fitting and the alloy that would made up the tube and the alloy that I tried to put in there, all of those are going to try and give up heat and contract, but they're not all going to contract at exactly the same time, and I stand the ability of fracturing the solder joint all the way through from the face of the fitting to the back of the fitting, which would set me up for a leak pad. What do we need to be aware of when we're making these new no-lead solder joints? The cleaning procedure for the tube and fittings is the same for the new no-lead alloys, the same as what we should have been doing all along for copper tube, wrought copper fittings, and the older cast copper fittings. The oxides have to be removed from the tube and the fitting. You can use sand cloth, nylon abrasive cloth, plumber's cloth. But the fitting surfaces have to be mechanically clean. It's extremely important that those oxides are removed. The other thing is the type of flux and the type of solder. There are solder flux combinations out there, and there's enough guys on the webinar that realize that there are certain solder flux combinations that don't work well, even copper to wrought copper fittings. And there are solder flux and solder alloy combinations that don't work well with the new no-lead copper alloys simply because of the higher melt temperatures of some of those alloys, solder alloys, not the fitting alloys. What's extremely important is that the heat is applied correctly from the base of the cup to the front of the cup, so that the flame washes out over the tube, so that we can maintain enough heat in the tube, the fitting, and the capillary space so that we continue to have that molten alloy flow to the back of the cup. And the other big thing is to try and make sure that you don't overheat the joint. The greatest problem that we see is most mechanics are using way too much heat to begin with, and with the newer no-lead alloys, it causes a little bit more problem when you use way too much heat or way too big of a torch to make the joint. They just tend to overheat. Once they overheat, you burn the flux. Once you burn the flux, there's no way you'll make a satisfactory solder joint. The other one is never quick quench the joints. Cool, normal heating is the best, or cooling is the best way to go. And I get a lot of questions about, can we really make good solder joints in these newer no-lead alloys? And the answer from CDA obviously is certainly with the proper application of heat and a proper soldering technique. Proper training is an extremely important thing. CDA provides training programs all over the U.S. Now we were able to do a lot more when we had a lot more managers in the field, but we get around as much as we can to do as many training programs as possible. If we were to look at some of the testing that we did, if we took no-lead, this is a 2-inch no-lead copper alloy ball valve. You'll notice that this one's tagged. It says it doesn't have any greater than 0.25% lead in the wetted surfaces. It meets the requirements of NSF 61 NXG or NSF ANSI 372. It's a no-lead copper alloy valve. This is what it looks like coming straight from the factory. You'll notice what we did. We cleaned it so that we had a nice shiny appearance on the inside of the fitting cup. We cleaned the tube. We applied a very thin, even film of flux on the tube, a thin, even film of flux on the fitting, and we made a solder joint in accordance with the heating and solder application procedure shown in ASTM B828, which I went through rather quickly, but this was the final joint. You'll notice that there's no cap on this because it makes no sense to put a cap on a solder joint because it adds no additional strength. All of the strength in a soldered joint is what's in the capillary space, not what we put on the outside of the joint. So we took that joint, that valve, we took it apart. You'll notice that the Teflon seat at the top where the valve stem came out isn't damaged at all. You notice we got more than 100% penetration, which we got very good fill. You notice a dull gray color here, dull gray color there. This area right here, if we were to flip this over and match it up, what it did was it actually separated the solder from the solder. We had almost 100% penetration with 100% fill in this particular joint. Use the ASTM B828 standard, using the process that should be done for any solder joint, and we got very good coverage. And last but not least, it can be done. Well, I see one question here that asks about what about an RPZ backflow for makeup water? And if we were to look at the what's actually listed in the new Reduction in Lead Act, if the water that is flowing through that reduced pressure zone backflow preventer is only being used for makeup water for a boiler or for what we would call a process application, it could be a leaded alloy material. If the stream of that RPZ, they're going to take any water off of that line and use it for human consumption, then that RPZ would have to meet the no lead law, because some of that water would be used for human consumption. Now I see one there says, OD Corporation is the only flux company that I am aware of that has put in writing what flux you should use when soldering lead-free copper alloys. They specify a pre-tinning flux. Are you aware of any other flux companies that are recommending what flux to use when soldering lead-free alloys? I would have to say that I am not aware of any of the other manufacturers, flux manufacturers, saying exactly what flux to use. The testing that CDA did, we used a number of different fluxes. All of those ones that we used were ASTM B813 water flushable fluxes. The solders that we used were no lead solders meeting ASTM B32 section 1, which means they're no lead alloys, and we got perfectly good results with almost all of those. So for to say that it has to be pre-tinning flux, I'm not aware of that. I know that there are valve manufacturers out there that are suggesting other flux solder combinations other than pre-tinning. So to provide an answer that that's the only one, I would be providing false information if I said that that was the only approved flux to use for making no lead copper alloy solder joints. Yes. Another question just popped up. It says, I have been trying to find the publication on soldering lead-free valves on your website and can't find it. If you go to copper.org and go to applications, go to plumbing, tube, and fittings, you can go, or you can go into publications. The publication number is A4108. Recommended practice for making solder joints in no lead copper alloys. Additionally, there is a video in our DIY section of videos that provides the video based on the testing that CDA did for soldering of no lead copper alloy valves. There again, that one can be found directly off of the piping page at copper.org.